Once we reach halfway to the equivalency point, something really weird happens. Um, it's really important that you can kind of pick out when this halfway point happens because it's kind of the peak buffer range. When we're halfway, the pH is equal to the pKa, which really just means that if we go up to our figure up here, we learned about when pH is equal to pKa when the concentrations of the acid are equal to the concentrations of the base, which is what this says right here. The concentration of the acid is equal to the concentration of the base when you reach halfway to the equivalency point. So if you look up here in our diagram, we have 1, 2, 3 HAs, 1, 2, 3 A minuses. So we are halfway to the equivalency point, and the concentration of those two things are equal. That is why the pH is equal to pKa when you're halfway to the equivalency point, which is up here. All right, so when you're doing the calculation for when we're halfway to the equivalency point, you kind of have to prove that we're halfway to the equivalency point. Now we're still in the buffer range, which means we still have to do the stoich first and then work from there. So that's what we're going to do. First, we're going to do the stoichiometry first. So we've added 25 milliliters of the sodium hydroxide to that 50 milliliter sample of the 0.1 molar HCN. So we, once again, do the titration equation first. HCN plus OH minus, once again, we're going to kind of make this the net ionic, not equilibrium. That's going to be making H2O, which is a liquid, plus CN minus, which is aqueous. So we're going to Rice table it. So to begin with, we still have that 5 millimoles. All right, now we have 25 times 0.1 millimoles of the OH minus. That is 2.5 moles, millimoles of the OH minus. We don't care about the water. And this is 0 over here. Minus x, plus x. So this is still going to be the limiting, the OH minus is still going to be the limiting reactant. If it's the limiting reactant, we're going to have 0 of it at the end, which means that x for this is 0.25. Plug 0.25 in for everything, in for x, so this is, oh, excuse me, 2.5. 2.5. This is 2.5, and this is also 2.5. Hey, look at that. This is why we know that the pH is equal to the pKa when we're halfway. The concentration of the weak acid is the same as the concentration of the conjugate base, and that is something special, and that's the pH is equal to the pKa. Now, if you're doing a problem like on an FRQ or something like that, you can just simply say because they're equal, pH is equal to pKa. That's something completely valid if you want to do that. I'm still going to show you the quack table, and it will make sense once we do that as to why that happened. So we have 0.25 of both of them. So we're going to write out our still acidic equation. All right, we have in our quack table, we have 2.5 millimoles of this and 2.5 millimoles of that. 0 of this, we don't care about the liquid, minus x, so 2.5 minus x, plus x, and plus x. All right, we're going to plug this into our k expression. So we have 6.2 times 10 to the negative 10th is equal to x times 2.5 minus, or plus x, divided by 2.5 minus x. What can we say about those x values? We can say that x is less than 2.5, so it's negligible. Okay, so then we have 2.5 divided by 2.5. Those are going to cancel out. So x is 6.2 times 10 to the negative 10th. And remember that x is equal to the H3O plus concentration. So pH is equal to the negative log of this value, which is the Ka. And all you have to do is the negative log of that. So 9.21.